Solving systems of equations using elimination. A system of equations is two or more equations whose solution is the point of intersection on the graph of the system. A system of linear equations is two or more linear equations, so their graphs would be straight lines. A system of linear equations can have one solution if you have two intersecting lines. The solution would be the point of intersection. A system can have no solution if you have two parallel lines. There is no point of intersection for two parallel lines, therefore no solution to the system. And a system will have infinitely many solutions if there are infinitely many intersections, which means the two lines are always intersecting. We call that coinciding lines, which basically looks like the same line. To solve a system algebraically using elimination, we want to combine like terms in both equations so that one variable will cancel out. Sometimes we might need to multiply one or both equations so that this will happen. Remember, whatever you do to one side of the equation, you must also do to the other. In our first example, when we add like terms or combine like terms, we will see that the y's will cancel out. 4x plus 2x is 6x. Negative 3y plus 3y is 0. And negative 2 plus 26 is 24. From here, I simplify the left side and then solve for x. So the x value of the solution of our system is 4. Since the solution to the system is a point, we must also know the y-coordinate. If I know that this point is a point on both of these lines, I can use one of these equations using x equals 4 to find the correct y value. It doesn't matter which equation I use, but I chose to use the second one. Now if I know that 2 times x plus 3y equals 26, and knowing that x equals 4, I can substitute 4 in for x and then solve for y. So my solution has a y value of 6. If I've done all of my math correctly, then the solution should be the point 4, 6. And this represents the point where the two lines intersect. If I'm not sure of my answer, or I want to check my work, which I should always do, I can always take this x and y value and substitute it in for both equations and make sure that I get a true statement. Remember, the solution is the x and y values together that make this left side of the equation equal to negative 2. And for the second equation, they also make this left side equal to 26. The top equation says that 4 times my x value minus 3 times my y value should be negative 2. With a point of 4, 6, that would be 4 times 4 minus 3 times 6 should be negative 2. So when I get a true statement, negative 2 equals negative 2, that means that this point is on this line. So it is a solution for the first equation. Now, in order for this point to be a solution for the system, it has to work for both equations. So I will do the same thing, but plugging 4 for x and 6 for y into the second equation. Once again, my point works in the second equation, which means that since it worked in the first equation and it worked in the second equation, then this point is a solution to the entire system. When I look at this system, the problem that I run into is that none of the variables will cancel out. 6c plus 6c is 12c. 7d minus 2d is 5d. I want one of them to cancel out. So what I'm going to do is multiply the second equation by negative 1. The first equation is untouched, but the second equation has all opposite signs now. By multiplying the second equation by negative 1, when I combine like terms, the c variables will cancel out. 6c minus 6c is 0. 7d plus 2d is 9d. And negative 15 minus 12 is negative 27. Now I have an easy equation with one variable that I can solve. So d in my solution must be negative 3. When your variables are other than x and y, when you're writing your point, you should always put them in alphabetical order. So my point should be c, d, which means that my solution will have a second coordinate of negative 3. If you've altered the equations at all, like I have done here, when you're trying to find your other variable, you should always use the original system. This is just in case we made a mistake when we were multiplying. This time I'm going to use the first equation for no reason other than I felt like it. And using d equals -3, we substitute -3 in for the variable d. And then simplify to solve. And we get c equals 1. So my solution for my system of equations should be the point 1, -3. By substituting 1 for x and -3 for y into both equations, I find that the left side equals the right side for both equations, which means that this point is the intersection of the two lines. Sometimes solving a system of equations by elimination requires manipulating the equations and also knowing which variable you want to cancel out. Remember, in order for a variable to cancel out, they must have the same number but opposite signs. For example, in order for this 10y to cancel out, I need to add it with a -10y. Unfortunately, the other y has a -5 in front of it, so it won't cancel out right away. But if I multiply the first equation by 2, now the y value has a -10 in front of it. And if I combine that first equation with my original second equation, the y's will now cancel out. If you're multiplying one of the equations in order to get coefficients that will allow you to cancel out one of the variables, what you need to remember is that if I need to multiply this -5y by 2 in order to get -10y to cancel out with a +10y, I must also do that to the rest of that same equation. I can't just change one of the terms. Every single term must be multiplied by 2 in that equation. Think of it like a seesaw. When the equation is given to me, my seesaw is balanced. But if I were to change one thing on one of the sides, the seesaw would be unbalanced. So what I do is make sure that whatever I do to one side, I do it to both sides so the seesaw stays balanced. Let's get back to the problem. Now that I have y's that will cancel out, I can add like terms in both equations. The y values cancel out nicely, and I can solve for x by getting x equals 7. And remember, you need both variables in order to give the solution, because the solution is a point, which has 2 coordinates. If I want to find the other coordinate, I must use this x value back with one of the original equations. So I'm going to use anything that's in white here, ignore all the red, and use only one of these equations. I don't need both. This time I'm choosing to use the second equation for no reason whatsoever. I could have just as easily chosen to use the first equation. In the second equation, all I'm going to do is change x to 7, simplify, and solve for y. And I find that y equals 1. So the point of intersection for this system of equations should be the point 7, 1. And I can confirm this by substituting x as 7, y as 1 into both equations and seeing that the left side equals the right side. So the solution is 7, 1. Now up until this point, every time we check our point, it works. It's a correct solution. What happens if your point that you're checking is incorrect? Before I made this video, I solved the system and got the solution 7, 10. When I checked my point into the first equation, I got a statement that wasn't true. The left side came out to -22 and the right side came out to 23. -22 is not equal to 23. That indicated to me that maybe I made a mistake somewhere up here, so I checked my work. I noticed that I didn't make any mistakes when I multiplied or subtracted, so then that tells me that there must be a mistake with this point, 7, 10. And sure enough, when I went back, I realized that I divided incorrectly and the point should have been 7, 1. And this is why it's always important to check your answer. If you get a statement that is not true, meaning some number equal to some different number, then you know that there must be a math error somewhere, either in your checking or in the solution that you're checking. Elimination will work, meaning a variable will cancel out, if its coefficients are opposites. Remember, the coefficients are the numbers in front of the variable. So if I have one equation with 2x, the other equation will need to have a -2x in order for me to be able to cancel out. In this system of equations, if I wanted to cancel out the x's, what coefficient would I need to have in the second equation? The second equation would need to have a coefficient of -3. In this system of equations, if I wanted to cancel out my y variables, what coefficient would need to be in the second equation in order for my y's to cancel out? The second y variable would need to have a coefficient of +8 in order for the y's to cancel out when using elimination. So if we're given a system that has coefficients that are not opposites, we'll need to make some adjustments. Let's look at one last example. Notice that in this system, if I tried to combine like terms, neither the a's nor the b's would cancel out. So I'm going to need to make some adjustments. You can choose which variable you want to cancel out. Let's say that I wanted to cancel out the a's. If I have 3a and 5a, in order for them to cancel out, they need to have the same number with opposite signs, or opposite numbers. With 3 and 5, the number that I could get to is 15. So one of my equations would need to have a 15a, and the other equation would need to have a -15a in order for them to cancel out. To do this, I would need to multiply the first equation by 5 and the second equation by -3. This would give me coefficients that are opposites. Now let's say, for example, that I wanted to cancel out the b values. With coefficients of 4 and 9, the number that I could get to would be a coefficient of 36. So one of my equations would have a 36b, and the other equation, in order to cancel out with that, would need to have -36b. In order to get that, I would need to multiply the first equation by +9 and the second equation by -4. Again, one of these must be negative. So if I have a +4 and a +9, one of the multiplications must be negative. I've decided to eliminate the a's because multiplying by 3 and 5 is much smaller than multiplying by 4 and 9. So I multiply the top equation by 5 to get 15a, and I multiply all terms in that equation on the left side and the right side. Then, since the bottom equation has a coefficient that's +5, I need to multiply the entire second equation by -3 to get the opposite of 15a, -15a, and continue multiplying across. Now I can combine like terms, and the a values will cancel out. Simplify the left side and solve for b. Once again, I'm going to use the original equations to find my other variable. Substitute -1 for b and simplify to solve for a. So the solution to this system should be the point 2, -1. Substituting this point in for a and b into both equations shows that the solution works for both equations, which means it is a solution to the system. To recap, when solving systems by elimination, your goal is to have opposite coefficients for one of the variables. When you have this, you can combine or add like terms so that that variable will cancel out, and then you can solve for the remaining variable. Sometimes, before combining, you might need to multiply one or both of the equations by some number in order to have opposite coefficients. Once you've combined or added like terms and then solved for a remaining variable, you're going to substitute that value into one of the original equations and solve for the other variable. And don't forget to check your solution. When you substitute the two variables into both original equations, you should get a true statement. If you only get a true statement for one of the equations, then it is not a solution to the system. The point must check for both equations.